solve this, right, get an expression for this, then I will be able to obtain what the partial molar entropy is. So this is equal to, we can break it down into steps. Let's imagine first bringing our pure I, call that step one, and that is bring 1 mole of pure I from whatever the pressure P is to whatever the partial pressure is that it will exert in the reservoir. Plus, then a second step is to bring it into the reservoir. Okay, we know how to calculate these things. This first one is going to be minus R log of PI over P. And the second one is because this can be done reversibly. I can move that I back and forth across a membrane permeable to I. So the entropy change there is just 0. And so what I end up with for this delta S is just minus R logarithm of, now look at this, yi. Okay. So I've got my result, and that is that the partial molar entropy of a component I in an ideal gas phase mixture is equal to the pure component value here minus logarithm of its mole fraction. So there's my important result. So the partial molar entropy here is a function of composition, and that's what it is. Now, the free energy quantities have entropic content, and so we would imagine that they also are going to have a dependence on this composition, so let's take a look at that. By far the most important of the two is G, so let's look at the partial molar gives free energy of a component I in a mixture, and I can write that out as partial molar enthalpy minus T times partial molar entropy. And for this, I know that I have HI0 and minus T times, and I've just calculated it here, that's SI0, little SI0 minus R log YI. So if I do this further, I've got HI0 minus T SI0 plus RT log of Y. And I recognize this thing as just GI0. It's RT log Y. So I have an expression for the partial molar Gibbs free energy. Now this is one of the most critically important properties that we're going to examine in this course, or in thermodynamics. And it's called, for reasons that we'll be able to understand here very shortly, it's called the chemical potential. And out of deference to Gibbs, who first considered this, let's use his notation. So what I'm going to do here is write the partial Gibbs free energy is going to be written mu sub I. And this is called the, bump there, chemical potential. Of component I in the mixture or solution. And then I'll write also GI0 will be written as the chemical potential here of the pure component, where the superscript 0 means pure. So the equation I've developed above says that the chemical potential of the partial molar Gibbs free energy of a component I in a mixture or a solution is equal to its pure component value here plus RT times the logarithm of its mole fraction. That would be, this is for ideal gases. And we can imagine that the relationship might be a bit more complicated when we go to a look at things other than ideal gases. So let's write a summation of the partial molar properties of ideal gas mixtures that define or describe the solution. Partial molar volume is equal to the pure component molar volume. And for ideal gases, we know that's RT over P, but let's keep it a little more general here. Partial molar entropy is equal to the pure component value. Partial mole entropy is equal to little SI0 minus R log Y. And finally now we write this in terms of our Gibbs notation. So this is basically the whole story. I could write them down for any other properties that I want constructed out of this. Let's remind ourselves this is for ideal gases. We next want to introduce the concept of molar property changes of mixing. Let's start out with volume here. And the notation I'll use is this. And what that means is the change in volume of a system that we experience when I create the mixture out of the appropriate amounts of pure components. So it's equal to the molar volume of the mixture here minus the summation of the pure component values. So you can use this as the definition here of the molar property changes of mixing for any properties. I've done it here for volume. Everyone clear on that? So I can write it out here in this case, because I can express that volume as I've done before, as here the mole fractions times all of the respective partial molar volumes. So that's equal to the summation of yi here times so that's, I haven't made any assumptions about the behavior, but for ideal gases, it's 0. Because the partial molar volume is just equal to the respective pure component molar volume. And I could make the same statement for ideal gases that the molar enthalpy change of mixing, that is also called the heat of mixing. And of course, if it were a solution, I'd write it in terms of x's. But now we can generalize it out. Let's look at what the molar entropy change of mixing is going to end up. You work that out for yourself. It's going to be equal to minus R times the summation here of yi log yi. And the molar Gibbs free energy change of mixing is going to be equal to RT times the summation of yi log yi. Once again, remind ourselves this is for ideal gases. So we've got these pretty well described now. Anybody got any questions about that before we're moving up? moving forward. So as far as ideal gases are concerned, now we have everything we need to know here in order to solve mixing or demixing problems. So I could ask myself to calculate the thermodynamic property change associated with mixing, say 2 pure gases, 3 or 4 pure gases, mixing a mixture with a mixture, demixing, and so on. All of those kinds of problems can be solved by breaking the process up into a series of steps. So that should be clear, so let's look at an example. I'm not sure I'm gonna have time to finish it, but we can at least get it started. So let's say I've got 1 mole of air. If that has a mole fraction of nitrogen, let's say keep a simple description here. And 0.22 moles of oxygen. And in another system here, I've got 2 moles of pure oxygen. So this is system 1, this is system 2, and there are some given temperature and pressure, and I want to consider the process where I mix them. You see I'm going to end up with 3 moles, and I can calculate using a material balance what the mole fractions of nitrogen and oxygen are. But what I'm interested in, this is at some constant T and P, I'm interested in calculating delta S for that mixing process. And the first thing I need to do is to use the material balance to solve for what these final mole fractions are. And if I do that, anybody got any problem with that? Do I need to work it out, or can I just write down what that is? The mole fraction of nitrogen turns out to be 0.26, and for oxygen turns out to be 0.74. So to solve this problem, calculating delta S, I break it up into 2 steps. So delta S1 is what I do to bring these, first of all, delta S1 will be to demix the air. So now I'll just have a set of pure components plus delta S2 mix the pure components. So if I can write that out, I have minus here, and this is now for system 1. Call this thing system 3 then. Well, the bell is wrong. Let me write the result here, and then we'll talk about it on Friday a bit more. Sorry. That the whole thing works out to 9.912 R. We'll talk about that more on Friday, but you get the idea here that we can solve any kinds of problems like this by breaking it up into however many steps we need to be able to solve for the final result. Now I want to be sure here to collect any of the unclaimed exams.